record on this computer. All right, so we're going to talk about chapter 3 probability tonight. Just kind of like give some context. A big chunk of tonight is really just kind of laying out the definitions and foundations so that we can start talking about distributions and what they mean, and so we can use them in terms of modeling and other things. So that's why I was saying before, it's sort of a necessary background information lecture, and so we'll revisit these concepts throughout the semester. So data still question. I like the ggplot kind of in the 1 minute papers. I thought that was good. If you're still having issues with ggplot, I revised the labs last summer, so you should be seeing as you work through them now, more ggplot. Like they used to all be base R plots, and now they should largely be ggplots. If you go through and you still see some base plot R's, and send me a note, but I think I caught them all. Just going through 10 labs is a bit much. So we're there. All right, so let's start with presentations. I think we have Matt up first. Are you here, Matt? I do not see Matt on the list. If you're here, speak up. If not, what about Donald? I see Donald. Oh, I have to stop sharing. I'll stop sharing so you can share your screen.
Mine's really quick.
I like quick.
So this problem said that they pulled some students in a statistics class, this is high school AP statistics, and asked them how many hours of television they watched in a week. And the sample yielded 4.71 hours is the average, with a standard deviation of 4.18, and it asked what shape the distribution would be. And because the distribution is going to be, they can't have said that there was less than 0 hours watched. There's a fixed boundary on the left side, so it's going to be skewed off to the right. And the standard deviation of 4.18 is almost as much as the mean, so it's probably very variable out to the right.
Great. Yeah, that was short. But being able to describe distributions is important. So that's good. All right. So I have Mark up next.
See if I can figure out how to share my screen here.
See here.
Share. Okay. Hopefully you can see sharing at this point.
Yep, I can see your screen.
Okay.
Play some Spotify.
Yep.
I didn't see what you're playing though.
Yeah, that's okay. I have to go back to that later. Okay, so I had this problem here. I think it was 233. It was basically to plot the box plot, but I guess I did it slightly different here. So I went ahead and put it into R. I did find I got a very slightly different numbers here. So you'll see it when you do the plot, but basically the box plot, if you're doing it manually, you're looking for the interquartile range, which is the 75% minus the quarter one. And then you're basically plotting those two, and then you're gonna go ahead and put the median down, and then look for the whiskers, which the max range would be 1.5 times the interquartile range, or the last data point of the min or max. And then you look for anything out of that would be the whisker length. So I did a couple other things I'll go through really quickly. I just did a distribution plot of the points. Let's skip that and kind of move down to the other things I did. So one, I did a plot where I actually plotted the points within the box plot. So you can also do that to show you the distribution of points here. This is the outlier in red. And then one other thing was interesting you can do with ggplot is I guess they call it a violin plot. So you can put your box plot in the middle. This shows the mean, your outlier with your whiskers, and you can also then see the distribution. So it allows you to compare different distributions if you wanted to look at distributions side by side. So that was all I did with that.
Great. No, thanks for doing the extra. Yeah, I like those violin plots. There's I'll try to find it. I think I have a tab open in one of my browsers. There's like a whole new package on additional ways of looking at distributions. With, box plot is like one of them, and you can kind of split like one way on the right and one way on the left, and which are really kind of handy. But this early in the semester, I didn't want to overwhelm people, but I'll throw the link in the Slack channel. And then we have last but not least, is it Letitia? Am I saying that right?
Yeah, Leticia.
Leticia. Okay.
All right.
And let me just make sure. Did Matt come on? I don't see Matt. Okay.
Can you see my screen? All right, it's visible.
Yep.
So I did question 2.34, and this was basically on marathon winners. It's showing data from female and male between 1970 and 1999. And we were I was asked to answer 4 different questions about the histogram and the box plot, and the distribution and what it looked like. For the first question, it asked what features of the distribution are apparent in the histogram and not in the box plot, and vice versa. And basically within the histogram, you see the visual number of people finishing at specific times and the decline over time. There's 2 modes visible. So one would be for the male and one would be for females, and it's right skewed. For the box plot, you just see basically just a summarization of the distribution and the individual points. You can see the mean, and you notice the outliers as well. For question B, what might be the reason for the bimodal distribution? Basically, I said that it was based off the male and female finishing time. So you see those 2 in there. Question C, compare the distribution of marathon times for men and women based on the box plot shown below. I said that men's finishing times are lower than women's. For the men's, the outliers tend to end around 2.5 hours. And then for the outliers for women, it's closer to 3.2. And lastly, question D, they gave us a time series plot shown below, and it just asked to describe what is visible in the plot, but not in others. Basically, within this one, you can see the representation of the data set, unlike others where it wouldn't show the separation between men and women, or it's not clear the years where this data is being plotted. The plot shows representation of men versus women over the 30 years, and you can see the decrease between men and women in the time series plot.
Great. Thanks so much. Right, let's go here, get my chat back. All right. Cool. Well, thank you, everyone. So let's talk about probability. So this is really the only chapter in the book that I know the course has probability in the title. And so a lot of what we're going to do is related to probability, but in terms of certain events, like discrete events, until we get to the end, this might be the only night we're going to talk about it. And really we have to talk about this notion of probability models in order to get to the notion of a distribution, because the distribution is what we're often going to try to model and end up doing kind of predictions on. So that for something to be a probability model, there's essentially two key properties that we have to have. So we have to have some event, right, that we're going to be measuring. So we're going to talk about coin tosses a lot. We'll talk about rolling dice for now. But then we'll move on to talking about more interesting things, but we can kind of understand those. So I think it's a good place to start before we start trying to talk about, the probability of, a student doing their homework on time, right? Which is a different type of probability event that we could be modeling, right? But at least with a coin toss, if we presume fairness, we can kind of understand what we kind of have an intuitive sense of what we should get. And so we kind of want to we're going to play with that tonight and see, how often we get that. And then the other piece is that probability has to be between 0 and 1 inclusive, right? And so if something has a probability of 0, that means it would never happen. And if it has a probability of 1, it always happens, right? And then as we start looking at this, put this together, there's going to be some rules on how we do this. Now, there are sort of two kind of leading interpretations is the word I used, or kind of philosophies of probability. The vast majority of this semester will be revolving around this notion of the frequentist interpretation of probability. And so a frequentist is going to determine the likelihood of some outcome based upon the notion that event could happen, an infinite number of times, right? And we'll, that'll start to come clear tonight. And as we go through the semester, we're gonna, kind of reinforce that notion, right? The inferences we're making is based upon some kind of theoretical distribution or theoretical model where, we could say flip a coin an infinite number of times, right? That's what how the frequentist is coming to those beliefs or to those interpretations. Then there's the Bayesian approach, and we'll introduce Bayesian kind of ideas at the very end of the semester. For one, to kind of give you at least an introduction or kind of a taste of what that approach is, but also to contrast it with the frequentist approach to hopefully at the very end kind of really reinforce those differences. I think both approaches are used pretty widely in data science now. I think Bayesian interpretation is definitely growing pretty rapidly. And then when we talk about it, one of the reasons is it tends to be fairly computationally intensive, because the Bayesian is going to interpret, the outcome based upon some kind of simulation, and as you go along. Okay, so if that is not entirely clear, the goal is by the end of the semester, maybe I should throw this slide in the final, introduction and say, can you tell me what the difference is between these two interpretations? But frequentist says there's some truth out there. If I could do this an infinite number of times, I see one, and I'm trying to connect to what that infinite is. That's where it is. The Bayesian is really going to say, well, what I observed is real. And so I'm going to do a simulation to see how often I would see what I actually observed. Okay. So that's kind of really fundamental, and that's probably good enough to get you through like a cocktail party now with non-statisticians, but we'll hope to hopefully reinforce that as we go through. Like I said, there's going to be a couple of definitions that we need to talk about here. So particularly when we get into the frequentist approach, although I think, this applies to some extent with the Bayesian approach when we're doing simulations, is this notion of the law of large numbers, right? Which just states that as more observations are collected, the proportions of a particular outcome. So here's some notational thing. So we're going to have, so here we're talking about the probability of some outcome, and with the little hat here over the P indicates that that's our observed probability. And of course, we have observed probabilities, but what we're really interested in is the probability of the actual outcome for the population, or in the case of a coin, what is the real probability of getting a heads or tails, right? The real probability, which we just represent as P. We typically do not know the real P. And so we're using the P hat, our actually observed, to estimate that true P. So in the law of large numbers says, as we collect more data, right, that observed probability is going to converge to that outcome. So, so here's an example. So if we're tossing what is presumed to be a fair coin, right, it comes up heads the first 10 tosses. What do you think the chance of another head will come up in the next toss, right? Is it 0.5, less than 0.5, greater than 0.5, or 0.5, right? It's going to be 0.5. I saw Mark kind of mouth it, right? So this kind of leads into this other notion, right? So because of the law of large numbers, if you believe that, well, we should have half heads, half tails, but each event is independent, right? And so if you think that, if you thought something other than 0.5, right, this is something called, the gambler's fallacy, in that, oh, I must be due for a tail because I got a whole bunch of heads, but that's not the case, right? So don't confuse the law of large numbers for saying something should come out. I actually have a little Shiny app. You can run this from the Data 606 package, and you can kind of see this here. So there are a couple of parameters that we can look at on the left side. So I have it, if you load it up by default, this here is set for 100 games, and odds of winning is 1 out of 2. So the notion here is like 1 out of 2 would be like flipping a coin. If we want to look at like rolling a dice and getting like a 1 is winning and then 2, 3, 4, 5, or 6 is not, right? So you can change these, but let's just stick with the coin toss, right? So if we do 100 coin flips, right, in this particular run, I ended up with 16. So if we say we're going to add 1 if we get a heads, and we're going to subtract 1 when we get a tails, we ended up with like 16 more heads in this particular run, right? And I can click start over. Now we ended up on the bottom side, right? And we're going to end up all over the place, and there's a number of runs. So I could say, well, let's just do 20 at a time, right? And next week, I'm going to allude to what we're going to do next week. We're going to start looking at, well, where are we at the end of that outcome? If we just did 100 trials and we did 20 of them, right? So this 0.5, right, we would expect to land on 0.5, right? And so what we're trying to do is now build up the language and the tools to say, in the case of flipping a coin, right, we know we should expect there, but at some point we're not going to know where that expectation is. And so we're going to have a whole bunch of these trials, and we want to say something like, how sure are we actually observing, right, that actual probability, right? So we're going to look at those outcomes, but we'll look at it next week. But so we can do this over and over, and you can get, you're going to end up at different places. Notice that we tend to be between -10 and 10. So let's just think about what the possible range of outcomes could be. If I only got heads, right, I would add, and I could end up at 100. If I only got tails, I would end up at -100. So if we look at this plot, the actual range on the y-axis could be -100 to 100. But of course, ggplot is just going to go far enough to do it. And if I do, okay, so, well, we went a little bit above 10 on this one. Here, okay, here we go. We ended up at 15, right? So, is that, and so some of the questions we want to ask is, getting 14 maybe give us evidence that the coin is not fair, right? So we can do this over and over. So I actually have a couple of slides here, right? So here's one particular run, right? And here I did it up to 1,000, right? And this is sort of the R code that's kind of in the back end of this Shiny app, right? And so here in this case, right, I'm the range on the y-axis is -15 to 15, right? And it looks like we have a lot of variability here, right? We're going up and down and kind of, man, it's just all over the place. And we ended up, I don't know, somewhere around 6, right? But again, what is the theoretical range this could be? Could be 1,000 to -1,000, right? So going from this slide to the next slide is my little attempt to try to depict the law of large numbers. So let's do that. So here, now I fix the y-axis to -1,000 to 1,000, right? So this is that notion of convergence, right? I mean, convergence is a very technical thing in terms of like calculus, right? We talk about convergence and divergence, and we'll kind of talk about that a little bit later when we talk about certain distributions and when we use distributions to actually, get confidence or probabilities. But right, this is kind of what we mean, right? We do more trials and it's going to kind of converge to what the true probability is, right? And so ending up, right, with 5, probably at least intuitively right now, and we're going to kind of define this a little bit more using statistical terms, but right, that getting 5 more heads than tails doesn't seem so unreasonable if you flipped a coin 1,000 times, right? So how far does that have to get before we get there? So these are kind of the foundations for how we're going to start to build these models. All right, another quick definition, right? So we need to start putting these together to talk about, distributions, right? Is where we're trying to get. And so it's how these distributions are going to be put together is going to in part be determined on the type of outcomes we have, right? So we have disjoint and non-disjoint outcomes. So disjoint meaning that they're mutually exclusive. They cannot happen at the same time. And then non-disjoint means that they could happen at the same time. And so how we build models will kind of depend on that. So now let's get into the distribution. So when we talk about a probability distribution, we're really just talking about a list of all of the possible outcomes that could occur. So for a discrete outcome, like a coin toss, it's pretty easy to kind of list this out. So the probability of coining a coin toss, right? So we have some probability. So what's the event is the coin toss. We either get heads or tails, and heads is 50% likely, tails is 50%, right? And so some key components here for a distribution, right? The events listed must be disjointed, right? They have to be mutually exclusive. And the probability must be between 0 and 1. And the sum of the probabilities must equal 1, right? So we're covering all the outcomes. So we could extend that, right? What's the probability distribution for 2 coin tosses? Well, we could get heads, which is 0.25. We could get tails then tails, which is 0.25. Heads then tails, and then tails then heads, right? Each of these is between 0 and 1. They're all, these are all disjoint, right? And the sum of all the probabilities is 1. So this is a proper distribution. So this is going to be the pattern we're going to use. Now this kind of gets convenient, right? Because when we don't know if they're disjointed, right, we want to check for independence. So we could kind of use some of these rules. When we talk about independence, right, so knowing that the coin landed on head on the first toss, it doesn't really provide any useful information determining what the coin toss on the second toss, right? Those are said to be independent. Okay, but in cards, right, this is where things get a little bit interesting. And right, if you know what the first card drawn from a deck and you don't replace it, that actually changes the probabilities for subsequent pulls, right? And this is sort of the foundations for counting cards. And there's been, why can't I remember the movie of the MIT students who were able to do this, go to Vegas and kind of just watch blackjack and by the fact that cards aren't replaced and they use multiple decks, but you can kind of say, whoa, geez, I saw a bunch of aces. So the probability of getting an ace is less right now, right? And that might change your bet. So those would not be independent outcomes. So we could do this to check for independence in situations where we're not sure. So here we have the results of, this is a general survey that's given. And this was a survey question where people were asked if they believe gun ownership protects citizens. And what we want to know is the response to this survey question independent of ethnicity? And so these are just some of the results. So from this survey, 58% of respondents said yes, guns protect ownership. I guess this was just in this particular data set from North Carolina. Okay, so we have respondents who were randomly selected in North Carolina, but if they were white, right, that was 67%. In other words, white respondents to this survey were 67% of them said yes. Black respondents was 28% and Hispanic was 64%. So the question is one's belief in gun ownership, is it independent of ethnicity? Right. So that's something we want to know, and we can get to that. So this is true, right? So if the probability of A occurs given that B is true, is equal to the probability of A given B is equal to the probability of A. So the probability of A in this situation is 0.58, and the probability of A given B, and we can pick any of these, right? So probabilities A is still right, that the A is the protect citizens. So given white, nope, not equal. Given black, not equal. Given Hispanic is not equal, right? So we would conclude that this is not, these two responses are not independent, right? And this might be a fairly useful, and actually something like this is I think particularly important to check for nowadays in data science, and if you're into polling. Nate Silver at 538 was kind of sort of the superstar data scientist for a while. I think some of his sheen is kind of falling away as his approach of aggregating polls. Essentially, he applied Bayesian methods in poll aggregation and placed weights is kind of fundamentally what he did. I mean, it's way more sophisticated than that, but what's happening, and actually I think Angela and I talked about this 2 weeks ago, this notion of measurement. So for him, like each measurement is a poll, and it turns out polls are getting increasingly inaccurate, right? Those measures are, the reliability of those measures are kind of decreasing for a host of types of biases we talked about like 2 weeks ago. And pollsters generally aren't answering that, right? The classic, one of the classic criticisms for a while now on polls is, I think some pollsters have changed this, but they used to only call landlines. I haven't had a landline in 15 years. So I never get called for polls, but I have started to get calls to answer these things. But anyways, that introduces a bias. And so we have all of these dependent measures, right? There's also kind of response biases, and then there's, and anyway, so this is becoming a problem. And again, I'm just trying to bring up another situation where as data scientists, I find data scientists are often just working with data that is already out there, already exists. But you need to start really thinking about the validity and reliability of those measures, and things like this in terms of like probability are really important. Oh, 21. Thank you. I just noticed. Yeah. All right. Moving on. All right. So I kind of alluded to this. I'm sorry. The dog is bored of my lecture. So I let her out. So we have two types of random variables. We have discrete random variables, right? So these are just things that take on integer values, number of credit hours, number of credits hours this versus last term. And then we can have continuous random variables, and these are kind of real numbers. So these are things like cost, cost of books, or, financial numbers, those kinds of things. And so, all right, let's look at another shiny demo. So give me a second to stop the other one and start this one. Oh, why does it do that? Always. There's something weird about Zeringen. Okay, let's look at another kind of little bit more complicated probability model. So actually, let's go here. So here, this table here is actually my probability distribution. And so this is actually based upon from years ago, but this was based upon scratch off tickets in New York State. So you can go to the New York State Lottery website, and they publish the essentially the probability distributions for each of the the types of lottery scratch off tickets they do. And so this is what it is. So here, so this is for $1 scratch off tickets. So the odds of winning $1 is 1 in 15. The odds of winning $2 is 1 in 11. Do not ask me why the odds of winning $2 is greater than $1. That's just what it was. All the way up to like the max prize you could get is $2,500. And that was 1 out of 618,000 tickets. Right. So this is, so we wanted to look at this, and I actually developed this. I had a student years ago who was a counseling psych. And so he was interested in doing research with people who are addicted to gambling. And so we were trying to figure out a way, is there a way that we can kind of address this notion of gambler's fallacy, because that's typically what those, I mean, there's multiple issues there, but gambler's fallacy is a big part of that. That if you could break that perhaps, or get people to kind of understand, maybe they would be less likely to keep buying tickets. And so we designed this so that really the only slider we have here is this number of tickets, which defaults to 365. The notion here, well, what happens if I buy one ticket a day? How much do you expect to have after a year? Right. And so you can see here, this is just running randomly, and you can see the values here that occurred once. You can see some bump ups. So at some point in the year, we won $30, but at the end of the year, we're down $136, right? Because it costs $1 to play each time, right? And so we can do this a whole bunch of times. So here's a time, maybe if we quit, 30 days in, we would have been up, but we ended up now $169. And so this little app, you could see the previous runs are kind of getting there. So that question I was asking, like, now the question we want to ask now is like, well, what should we expect to get after a year? Right. So we can do this a whole bunch of times, and every look at, every couple of semesters we get one that's above. So we hit the $100. But see, I have this button where you could do 10. Oh, we got the big one. We won like 2,000 here or something. Anyways, so we could do this, but you see the vast majority is down here, and we did well. I don't know how many we've done. I think we've done a lifetime now. And 1 year we ended up way ahead. But so our goal, right, and here's the histogram. So we can see of all the outcomes at the end of the year, right, twice we ended up above 0, right? And this dashed line is the average. So I guess I did 66. So if you live to be 66, you would have lost $119 per year if you did this, right? So this kind of introduces this notion of expected values, right? And that's a lot of what we're going to do. We're often interested, based upon the law of large numbers, we're going to observe these things, and we want to know what that is. And so this is also we talked about the mean in terms of descriptive stats a couple of weeks ago. This is also a type of mean, but it's the mean from a particular distribution. And so to write this out, let me just quickly, so it's a mean, but we're often going to write the expected value of some outcome, right? So X is our event. If you don't remember, this little Greek symbol sigma here is really just a for loop, right? You can think of this as a for loop. If you're more of a programmer, we're going from 1 to K, which K is the number of events we're doing. And the sigma is going to be a summation. There's another one, I think it's phi, that would be multiplication. So what we're doing is taking the probability, right, for that event. The outcome of that event, right? So in the case of the lottery ticket, right, could be the winnings, right? Times the probability of that event occurring, right? And so if we do that, we can sum that up and kind of get the expected value or the mean value. So let's start with a simpler example, and then we'll come back to the lottery example. So here's a silly little game where in a card game, you're going to win $1 if you draw a heart. You're going to win $5 if you draw an ace, including the ace of hearts, right? And that'll be important, right? Because remember, these need to be disjoint, right? So we have to kind of account for the fact that aces could also be hearts. And then $10 if you get the king of spades. And if any other card, you get nothing. Okay, so it's nice to write this out in the table. So the probability we get a heart, so the event of a heart, not ace, is 1, or we're going to get $1, right? So that's the outcome. So we have 1, 5, 10, and 0. Okay, so the probability for a heart, not an ace. So there's 13 hearts, right? But we're gonna exclude the ace. So we have 12 out of 52. An ace, there are 4 aces, right? So there's 4 out of 52 cards in the deck. King of spades, there's 1 king of spades. So the probability is 1 out of 52. And then anything else, there's 35 cards left out of 52. And you get 0 here, right? So if I add up this column, right, that equals 1, right? That, in order to have a proper probability distribution. So to get the outcome, right? So we're going to take the outcome times the probability of the event. So we're just going to multiply 1 times 12, 52. We get that. 5 times 452, we get 20 over 52. 10 over times 152, we get 10 over 52. 0 times this is 0, right? If we go back, all we're going to do is sum those up. We sum that up. So the expected value is 42 over 52, which is approximately 0.81, right? So if it costs nothing to play this game, right, you should win on average 81 cents, right? If you play it a whole lot of times, you should end up with, an 81 cents per run. So from a gambling point of view, right, if you had to pay $1 to play this game, you're expected to lose 19 cents each time you play, right? On average is what we're saying. And so this becomes a really important thing. And you can use this if you're interested. You could start digging into the probability distributions of Vegas games, and you'll find the expected value is always negative, right? If I were to take 1 minus this, if it was $1, right? So the expected value would be minus 19 cents. All of the games in Vegas have negative expected values, which is why they exist, right? You are expected not to win when you go to Vegas on average. Of course, some people do. And what the casinos hope is that, oh, you see those outliers, and that may be a whole other rant I'll do at some point in the semester on sort of our obsession with outliers. But my hope is through this course, you become more aware of that you shouldn't rely on them. Right. And this is what the distribution looks like. So there's a discrete random variable. So we could see the most common outcome is getting nothing. Here's winning $1, winning $5 and $10. Of course, 6, 7, 8, 9, and 2, 3, 4 are not possible in this game, right? But to kind of show this, and so this is a discrete random variable, right? Because there's a count, but this is the full distribution. We can kind of see the probability of each outcome, and we're going to keep doing this a lot as we go through the semester. Let's go back. Okay. So let's look at the lottery one, right? So one approach we could do to the lottery is do it with simulations. Like some of these probability distributions might get a little bit complicated. This one's not too bad because we can do it both ways. Or actually, let me show it this way, right? So we could use the formula notation, right? So I have the winnings, I have the value, and I have the odds. So we can multiply across. We get the X times the probability of X and sum that up, right? And so and then you have to take the $1 for paying it. So the theoretical expected value for our lottery is you're expected to lose 38 cents per ticket, right? Occasionally you'll be up, but on average you're going to be 32. But we could do it through a simulation. For those who are learning R, this might be kind of a neat little example. So here I'm just creating a data frame with the tickets. I just rename them, and I had to make sure that they came in as integers. So I just converted them to integers. So what I'm going to do here is I'm going to randomly sample a number between 1 and the max odds, which turns out to be 618,000 here. Okay. And I'm going to do that 1,000 times with replacement, right? Because I could potentially win, what was that, $2,500 twice, right? Because they're supposed to be independent. So I have replacement. So that's all this is doing, is sampling a number between 1 and 618,000 1,000 times. So this odds becomes a numeric vector in R, length 1,000 with a number in between those ranges. Okay. The vals is what we actually got, right? So I'm just going to repeat -1 for 1,000 times, right? So odds is 1,000. So these two things match up. And the reason why I repeated -1, right? Because it costs $1 to do each ticket. So that's sort of the base. So for each row in the tickets, okay, I'm going to look at this odds column, and I'm going to do something called a modulus. So I'm taking the odds. So I got this random number, and if I divide by the odds, so initially 15, and I get 0, right, meaning the remainder is 0, so the number I got was evenly divisible by that, I'm going to assign the values that, the value here. So $1 -1. Okay. If we go to the second pass, and I'm going to divide, well, let's go to the third one. I divide by 62, I get it. So if I get 62, 124, 186, right? Those would have a remainder of 0. So I'll set the value equal to 4. Okay. And I do that all the way through. And here I'm looking at the first, so we could see we lost $1, lost $1. Oh, he must have won $2 and then lost a bunch of dollars. But I did this 1,000 times, right? So in this case, I got a mean of negative 0.79. So in this particular simulation, I would expect my reported predicted value would be, oh, you would lose 7.9 cents, right? Versus our 38 cents. So this is a pretty bad simulation. If I could redo the slides and get a different answer. I'm looking at the distribution here. Oh, it looks like I got the 500 here, right? Which is kind of, because I'm taking the mean, right? And remember, the mean is not robust to an outlier. So that outlier really kind of skewed it. But anyways, because I have this data and I kind of know these, these probabilities, I could do it through simulation, or I can do it using the expected values if you have all the information. But I find this a really kind of powerful approach. You can see, like with the lottery, like this kind of stuff. Whenever I encounter these kind of problems where I'm trying to figure out what's going on, writing a little quick for loop to kind of simulate some data based upon what I actually do. So here I just want to simulate playing a bunch of lottery tickets. And anyways, so that's what we get there.
Are you sure your odds are coming out right though?
I'm sorry, Charles, can you speak up?
I was saying that because you only pick a number between 1 and 618,000, the probabilities might not match up if there's not all common factors. Like the odds of the $1,500 prize wouldn't be correct because it's not.
Well, you have 1 in 375,000 to get there. I mean, I guess I use the max of 618. I think you're right. I could use a larger.
The only way to get 1,500 would be to draw 375, 214.
Yeah.
Number, but that's underrepresentative for the odds. For
that prize. Yeah, you might be right. That might be why this never came out this bad. But let's.
Like you would need to find the greatest common factor of all of those things.
Yeah,
that way.
You're probably right. I think you're right. I know you're right. Good catch. So if we do this, if I do that, I mean, we'll probably get closer if I just instead of doing max this 1, 2, 3, 4, 5, 6, we could just do like, is that 10 million? This should be closer, I guess. Let's see what this, of course, I have a blog post I'll put up soon about random numbers, because I don't think we talked about that yet, or setting seeds in R. Copy this. Why is that not going in? And I may not have loaded ggplot. Oh, and really what I want to do is I want this thing, mean vals. See what this looks like. So here we got -442, but of course we can run this again. -28, -5.04. So we're hovering around there. What was the theoretical? -38. So we can actually have a distribution from our distributions, which is something we'll talk about later, sometimes called bootstrapping. The other law of large numbers, let me put another 0 on this. Let's see what we get here. There's 38. It looks to be a little bit higher. So yeah, I think you're right. So one way to do it is to multiply all the numbers, but I'm not sure. We'll probably end up with a number beyond the precision of R, I think, to get the largest common factor. Anyways, good call, Donald. All right. Here's yeah, we talked about that. Questions. We're actually going to end early tonight, perhaps. We'll put the
Could you go over again why you changed it to 10 million? I'm sorry.
So as Donald rightfully pointed out, by using 618,000 as the maximum, the chance of getting something evenly divisible by 375 to 14 is actually only, it can only occur once. So
Once.
yeah, so in order, so really the correct thing to do is to get the largest common factor of all these numbers. And one way to do it is just to multiply this column. But like I said, I don't think that number would be there, just to ensure that there is the proper probability that they could all occur.
Oh, okay. All right.
Yeah, it's so I wonder if I could do that. So I have this here. So tickets. Let me see here. So if I look at, I have no idea what it is. So if I do, so I think if I do sapply tickets, oh no, how would I do this? No, I don't think I need sapply. Anybody? Okay. Oh, so Preston's asked multiple. It is multiple, but if you take the product of all the numbers, that's guaranteed to be it would be a multiple of all of them, but it might not be the least multiple. There may be one that's smaller. So let me think here. Let me get a smaller example. Like, what's a multiple of let's say 2 and let me think here. No, what about 3 and 9? So 3 and 9, you can multiply it, right? So you would get 27. Oh, actually 3 would be the multiple. Boy, this is stretching my, I should get my high schooler in here. He probably knows this better than I do at this moment. But if you multiply, it's going to be a multiple, but it might not be the least multiple. So that's the difference between that and the multiplication. But if I want to multiply all the numbers, I'm just having I can't think of, I mean, the brute force way to do this is to say, I could say, let me just call it M. If I start with 1, I could do it as a for loop. So if I say for I in 1 to number of rows in tickets, and I'm just going to say M is equal to M times tickets sub I odds. So what is M? Yeah, that is a very large number. But now if instead of that, I put M here. Oh, wait. Yeah. M is no longer an integer, right? So what is M? It's probably it's numeric because it's so large. So sample only works on integers. So yeah, I'm not even sure how to, it has to be a positive integer. So now the sample doesn't work. Anyways, this is an unfortunate digression. I'm sorry. So that's something you should be aware of too. Like I don't know what the integer precision in R is. I don't know it off the top of my head. Probably a quick Google search will come up with it. So, but R does have some high precision numbers. In fact, there are even add-on packages that you can have increased precision of your numbers. So R is 64 bits. So I presume the integer is 2 to the 64 precision, or it might be 2 to the 63. It would be 2 to the 63 because 1 bit would be for the sign. So I don't know what that is. So what's 2 to the 63 is a large number. And yeah, so we can see just comparing. So the precision for an integer in R is, 9 times 10 to the 18, and M, our calculation of that product, is 5 times 10 to the 32nd, right? Which is why I got converted to a double. Anyways, a little digression for the computer science people out there. Any other questions? Going once.
I'm wondering if you could go over the R code,
Sure.
just of the graph.
Which the graph, like this graph?
Or I mean,
Or-
even the data frame, I guess, just to start, how you made the,
Yeah, there's probably better ways now with Tibble. So yeah, let me do it, break it down. A couple of like little tips for you in RStudio. So you can always highlight fragments of R code. And if I hit here, I'm hitting Command Enter. I'm on a Mac. So if you're on Windows, it'd be Control Enter, or you can hit this run button. What's really convenient when you get these kind of more complicated nested statements to just see bits and pieces. So we can see, just so I could write this out this way, I'm creating a vector for each row, right? And then R bind is a row binding. So if I do this much, right? So now I have the R bind of a whole bunch of vectors. I end up with this. Now R bind is returning technically a matrix, I believe. Let's double check here. So if I type class and I paste that in, yeah, it's a matrix. Okay. So a matrix has to be, all the elements in the matrix have to be of the same type. Because I have a character, you see it made all these numerical values characters. So now I have this matrix, right? And then I convert it to a data frame. So I can get it like this, right? And I save that in the tickets. So if we look at the structure of tickets, we can see I have 3 characters, which is why I convert those to numeric. Oh, what? Because I didn't do the, and then I renamed the columns. So this is code I probably wrote a decade ago. There are cleaner ways to do it with Tibbles that I just don't know off the top of my head. But yeah. Does that help? It's good to kind of start looking at this stuff, but that's way back when I said I still have some stuff in the old,
right,
I'm
I
old.
remember.
I'm old, so I still have a lot of base R stuff, and I'm trying to do stuff in new R. But I have a odd relationship with Tibbles anyways, but I won't go into that tonight. And that's just because of I maintain packages that were written before Tibbles existed. Is the rest okay? This makes sense.
Yep. Yeah. I got the rest.
Here's another little thing. You'll see I'll use for loops quite a lot and to do things. I should give a little bit of a disclaimer that in R, because R is a vectorized programming language, for loops are not particularly efficient because R will actually make lots of copies of the, it's essentially creating a new environment on each pass of the loop. So there's a whole class of apply functions that will essentially, you could do this like in a vectorized format. However, I find even for programmers, because most programming languages, for loops are pretty natural. And once you kind of get a notion of this, and if you look at it in conjunction with like essentially this sigma, if you start thinking of this sigma as a for loop, right? It just is just a mathematical notation for a for loop. We're trying to translate it here. And if you're new to for loops, right? So I is going to be set to initially 1. You're going to run everything in the curly braces. Then it's going to be set to 2, et cetera, all the way to the number of rows and tickets. So I'm going to use for loops a lot, but I feel like I should warn you that they're not always performant. And my sort of general strategy is it's, to me, conceptually much easier to write a for loop. And then I only worry about converting it to the vectorized format if it's like going into a package and I really care about the execution time. For just analysis, sometimes to me, a for loop that takes a little bit longer to run is a feature. It gives me an opportunity to go get a coffee because the computer time is cheap, But if it's gonna really tie me up, then I might want to do it. Oh yeah. Somebody's recommending the per package is another thing that's really useful. If you're really going down this path, and this is just like make a note, you know, of something you could look up when you need it. The other approach that people do is there's a package called RCPP. So you could implement just the for loop in C++, and R will handle all the, you know, it'll do the compilation. You can just embed the C code in like a RCPP function call. It'll pass the data in, do the for loop in C, and then bring the results back out, which is another way. If you really have to do it in a for loop, that's it. That's kind of a great way to do it. The other thing you can do is there's some really great parallelization packages. Almost everybody has multi-cores on their computers now, and so a lot of these problems, if it's just a simple, in this case, each run is independent of each other run, so we could just run them in parallel. If I have 8 cores, I can run 8 of them at a time and just combine the results at the end. But anyways, just like little tips that you can kind of save. Other questions? But get used to the for loop. If you're new to for loops, study that a little bit, because we'll use it a few more times.
Check those odds. If you just take the product of the last two, all the others are a multiple of them.
Is it really?
Yeah.
Oh, thank you. I'm gonna so if I say m is equal to, so you're saying 18,000 times 375,214, and then I make this m. Cool. Neat. So then if I take, I got to look at tickets again. So let's look at tickets. How do I want to do this? Let's just look at tickets. I'm sorry, we got 3 minutes. I could still end on time. So if we take m divided by, let's say ticket sub 1 odds. Cool. So that's even. Did you try this already, Donald?
Yeah, I checked all the other. Yeah, I put them all in a vector and divided it, and they all came out as integers. So.
Oh, that's so cool. How did you figure that? Do you have a system? It's been probably 2 decades since I've had to think about least common
I'm not sure it's least, because there's clearly the factor of 2 in both of them, but that was like the easiest way to get an actual integer.
Cool. I'm gonna update the slides before I post them. All right, everyone. If there aren't any other questions, we can call it a night. So I think next week, what is next week? Yeah, distribution. So kind of be an extension of what we're talking about tonight. I put the link to the 1-minute paper in the chat, so if you could just fill that out. Otherwise, I'll see you guys on Slack. And Angela will be on Slack. And we'll see you next week.
Good night.
Yeah.
Good night.